Okay, thank you. Yeah, so this is joint work with Gaia Carenini, who unfortunately could not come to give the talk, so I'm here. And yeah, this is going to be about automatability of tree-like Res-K, or k-DNF resolution. So what the question we're interested in is how hard is it to find proofs? So in general, we can think of a computer that perhaps runs some deterministic algorithm, perhaps randomized algorithm. It receives as input some theorem, and we wanted to output a proof of that theorem, right? And the question is like, how much time do we need for this? And so let's say that like P star is the shortest proof in some proof system S. And we know the running time has to be at least the size of the input plus the size of the smallest possible output. And the question is, well, can we do it in time polynomial in this, or quasi-polynomial, or what is the fastest time we can do in terms of this measure here? And in this case, we'll be interested in theorems that are saying that a certain formula is unsatisfiable. And we're looking at proofs which are refutations of this formula. So this is the notion of automatability, which is, we say a system S is automatable in some time f of n if it outputs proof in the system S in this time, this function of the input and the smallest possible output. Okay. So we're going to look at, well, let's start with resolution. And in particular, we'll be talking about tree-like resolution. So when the underlying DAG is a tree. And what do we know about finding tree-like resolution proofs? Well, we do have some algorithms like this DPLL algorithms that are searching for tree-like resolution proofs. This is a very simple algorithm. What it does is it chooses a variable to branch on, and it branches whether this is true or false. And it backtracks whenever it finds some clause of f that is falsified. So at some point, it will backtrack all the way, and we know the formula is unsatisfiable. And this algorithm, we can transform this search, this decision tree construction here into a tree-like resolution proof. Okay, so this is for tree-like resolution. And what we study in here is tree-like k-DNF, or Res-K. And this is very similar to this kind of search procedure, but instead of branching on just values of variables, we branch on conjunction of literals. Okay, so we can branch on whether x1 is true or false, and maybe we branch on whether not x2 and x3 is true or false. Okay, so in a very similar way, what we get here, we can translate this into this tree-like Res-K. And Res-K refutation, we can think of simply in the lines, instead of only having clauses, we have k-DNFs. Okay, and then we have some rules to deal with this, but we can think of like anything that is semantically implied would be sufficient. But we have just a generalized cut rule, an AND introduction, and an AND elimination. Okay, so what do we know about these systems? Well, for tree-like resolution, we know that we can actually find proofs in time n to the log n, so quasi-polynomial. And we've known this since the 90s. And the question is, well, is this the best possible algorithm? Can we actually be more efficient in finding proofs? And in the previous result, we showed that, well, under ETH, this is pretty close to tight. If we consider randomized ETH, which is this randomized exponential time hypothesis, saying that randomized algorithms cannot solve 3 sats in time 2 to the little o of n, then we actually show that this is tied up to constants and exponents. Okay, so this was for tree-like resolution. What about for tree-like k-DNF resolution? And a very simple generalization of that algorithm that finds tree-like resolution proofs in n to the log n, we can find tree-like k-DNF resolutions in n to the k log n. So we have an extra k in the exponent. So the result we had previously for tree-like resolution also generalizes to this study. So we know that if we could find these tree-like res k in time n to the literal log n, then RETH would be false. But is this dependence on k actually needed? Can we come up with a better algorithm, or can we show a better lower bound for non-automatability? And this is what we show in this paper. We don't get, we show a almost optimal. We have this extra log k here factor, but that okay, if we could automate in time faster than that, then RETH would be false. So that's the main result. Okay, so now the plan for the rest of this talk. Well, I'd like to show you what these algorithms are because they're very simple. I won't have time. I'll just flash something on the screen soon. Then I would like to say, okay, how do we actually prove this non-automatability result? And for this, I'll have to explain a little bit about Atzerias-Müller. They have this non-automatability for resolution, how this was generalized for tree-like resolution, and then what we actually changed in this paper. And then I'll finish with some open problems. So for these algorithms, the idea is we want this algorithm A that, given a formula and a parameter S, will find a refutation in time s to the log n, that n is the number of variables, as long as there is a refutation of size s, tree-like here. We're talking about tree-like resolution. And this algorithm, what it does, it's very simple. It will try for all possible variables and all possible polarities, whether if I restrict that variable to either 0 or 1, can I find a refutation with parameter s over 2? Okay. And if it does, then I can just do the other polarity with just size s and combine these two proofs. So it's a very simple algorithm. That's all it does. And if you analyze it, then you see that it actually takes time s to the log n. Okay. And for res k, instead of branching on only one variable, you're going to have to branch on k variables and k polarities. But the idea is the same. Okay, so that's all I'm going to say about the algorithms. So now we're going to talk more about the lower bounds. All right, so let's look at Atzerias-Müller. And if I do go too fast, please don't, please raise your hand. I will slow down. So what Atzerias-Müller shows is that if resolution is automatable in polynomial time, then P equals NP. And they show this by proving this. This is the main technical theorem, that there is an algorithm that will receive this formula F and output a new formula, A of F. So the A of F is a new CNF formula. It does this in polynomial time. And this formula A of F has this property that if F is satisfiable, A of F has a small resolution refutation. And if A of F is unsatisfiable, then there's no small, the smallest one is of exponential size. Okay, so it creates this gap between the size of resolution refutations. And now if you have this theorem here, then it's not hard to see that if you could automate resolution, you would be able to distinguish whether F is sat or unsat. You just run the automating algorithm on this formula A of F long enough so that as long as F is sat, it's guaranteed to produce a proof. And if it produces a proof, it's small, so it cannot be that F is unsat. So you can actually distinguish these two cases. Okay, so what is this formula A of F that they use? It's a formula that encodes that F has a small resolution refutation. Okay, so it gets a little bit meta here. So let's think a little bit about what this is saying. So I'm going to have variables encoding that there are S clauses. So I'm viewing my proof now in a linear format. There are S clauses, and I'm going to encode what this clause is with variables. So I have a variable saying, oh, which variables are is x1 present, is x2 or not x1, or what are the variables present. Also, I'm going to have variables encoding how this clause was derived. So for example, I could be saying that like, oh, this clause was actually a weakening of some clause of F. And maybe like this clause was, I obtained it by resolving over these two clauses. Okay, so I'm going to somehow encode a proof of size S of my formula F. So that's what A of F is. So then I have to include clauses that encode that this is actually a proof. So I will encode that I end up with contradiction with the empty clause, and that all derivations are sound, and they like preserve the order. So like the arrows are all pointing forward. I can't use something that it comes later on in the proof. Okay, so this is the formula A of F that they use. Okay, so I will talk mostly about the upper bound, because the lower bound, it holds for resolution. So it holds also for tree-like resolution. It holds also for tree-like res k. But the upper bound is where we get into trouble. But just to say one word about the lower bound, why can we actually get a lower bound when F isn't sat? And the main reason is that there exists some refutation. There exists this exponential size, like brute force refutation of F if F is unsat. So this will always exist. And the idea is that for the lower bound is that I can pretend that this exponential object actually fits into this polynomial size object here. And the way this is done is, well, I can even like layer this so that it kind of looks the same amount of layers. And then in a similar fashion as like pigeonhole principle, which we know is hard for resolution, I can pretend that like every row here fits into the row here. That would be like the general idea. Okay, so resolution can't tell these two things apart. Okay. Now about the upper bound. So for the upper bound, suppose I have an F which is actually satisfiable. So here's an example of an F that's satisfiable. And here I have an assignment x star where x1 equals 0, x2 and x3 equals 1. And I tell you that, oh, that there is actually a refutation, a small refutation of this formula. Well, there can't be because it's satisfiable. So how can you be convinced of this idea? So yeah, suppose someone claims that A of F is true, that is, there is a small refutation. How can we show that they're lying? Okay. So here's one way of doing it. I can ask, okay, in your refutation, you're saying you have a small refutation. Is the last clause the empty clause? Of course, you have to answer yes, because otherwise I already caught you lying. And then I'll ask, okay, how was it derived? So in this case, like, oh, okay, the last one is, this is what the refutation I'm pretending exists, let's say. So how was it derived? Well, it was derived by resolving x3 and not x3. So now I go to the clause which is falsified by x star. And as long as this was a sound derivation, there exists a clause that was falsified by x star, which in this case is not x3. Okay, so I move here and I ask you, okay, how was this clause derived? And then you'll say, oh, well, I resolved not x2 with x2 or not x3. Okay, I'll repeat. Okay, how I go to the clause that is falsified by x star, which in this case is not x2. And now it's, okay, how was this one derived? And again, you're going to say, well, not x1, x1 or x2. And now I can go to the clause that's falsified by x star, which is this one. And I ask you, how was this derived? And now you're going to say, oh, this was actually a clause of F. And now I caught you lying because I kept the invariant that my assignment falsifies this, but my assignment satisfies all the clauses of F. It's a satisfying assignment. So this cannot have been a clause of F. Okay, so this is exactly what the upper bound is going to do. And this works for resolution. Resolution can do this reasoning. Now, the problem for tree-like resolution is that is precisely here. How was it derived? There are too many options of how it's derived. And for tree-like resolution, I cannot forget anything. So I get a very large proof. So let me see if I can explain this a little bit. So if I tried to show why this would be large for tree-like resolution, I could look at this like layered version. And when you asked me like how is something derived, okay, in the beginning I can just fix it to some particular, like the beginning of my exponential size tree. But from there on, I will have like S over N options of how I derived this clause. And this for each of the N layers. So in total, I would be getting a proof of size S over N to the N in tree-like resolution. Okay. So I don't have this upper bound. And the idea to be able to get any upper bound which is non-trivial would be I need to decrease the options. There are too many options of how I can derive clauses. I want to decrease this number, which means I need to impose more structure in my formula. And I can impose any structure that I want as long as the lower bound still holds. So as long as I can somehow simulate some kind of pigeonhole principle there. Okay, so how was this done for tree-like resolution? So here's one way of imposing a lot of structure. So this doesn't quite work because I could just say that my proof is exactly this exponential size proof. Okay, I completely like have complete structure of what the proof looks like. The upper bound works in this case because if I have a satisfying assignment, I know exactly like which clause in the last layer is falsified by this assignment. And I can just ask you, okay, well, how did you derive this clause? And you can't say it's a weakening of an axiom because I satisfy all the satisfying assignment satisfies all the axioms. So I would have a very, very short proof that this cannot be a resolution refutation of a satisfiable formula. The lower bound will also work. So the only problem is that this formula is huge. It's of exponential size. And what I actually want is I want a certain trade-off between the size of the formula. It's not going to be polynomial anymore. It's going to be 2 to the squared n, and the upper bound 2 to the squared n. Yeah, and if I can get both the upper bound and the size of the formula to be 2 to the squared n, then I can get this non-automatability result for tree-like resolution. Okay, so in order to impose a bit less structure, but still enough, I can only restrict like the first squared n layers of this big tree. And now I'm going to add squared n these layers of triangles. So for each triangle, if I have the satisfying assignment, I will know exactly where to go on the bottom of this triangle. And I only have squared n different layers. So in total, I'm going to have the power squared n, which is the number of layers. And now how many places I can go to? If I add an expander with like degree delta, I will have like delta options per layer of where my assignments could be. Yeah, so this is just because I need to like reduce, otherwise my size will blow up. So I need to at some point reduce my big possibilities in one layer to the next layer. And there I can have an expander with degree delta. So this is what the expander looks like. And here, just to mention, this is where I need some randomness because I want to construct an expander with constant degree. And it's a very unbalanced expander, and we only know how to do this with randomness. Okay. So for tree-like risk K, the challenge is that I need to both decrease the size of the formula and the size of the upper bound. Okay, I need to save this square root K factor on both. And if I can do that, then I get the non-automatability result. Okay, so instead of looking at square root n, like fixing square root n layers, I can have a general parameter h. and I can do this same construction, but now the number of layers is n over h. And this I would like to be square root n over k. So I would like h to be large enough, like in this case, yes, square root k times n. But in that case, the formula becomes too large. And if I try to make the formula small, then my upper bound becomes too large. So I get this trade-off between formula size and my upper bound when I just try to do this strategy. So the idea is, well, I have this very big object, and we already argued that I can kind of pretend that big objects fit into small things. So this is what I would like to do. The only issue here is that the whole point of having this structure is that I can go directly to a leaf here without having to traverse many possibilities. And when I look at this small object, I'm going to try to pretend this fits into, how can I go directly to the position where my assignment can be? And okay, in order to do this, we need to add another expander. And the idea is, okay, each of the possible 2 to the square root kn assignments that I have will go to one of the d neighbors of this expander. So now I reduced it to only the neighbors of this expander. Those would be the options. Okay, again, I have the problem. I still have to encode a very big expander. So how can I actually encode this very big expander using only much smaller size? And I think this was one of the main ideas that we needed here, was that I actually I cannot encode the expander explicitly. I can only encode a circuit that computes the expander. And this is what the kind of, so we want to encode such an unbalanced expander, with size polynomial on the smallest side. And this is actually, we can actually do this and construct the circuit, which is polynomial on the small side, encoding this unbalanced expander. And we need randomness for this in order to get the degree down to like order k. Otherwise, we have larger degree if we don't have randomness. Okay, so the end formula looks something like this, where instead of like those triangles, I actually have smaller objects, and I also have these many of these expanders encoded as circuits for each evaluation I need. And in this way, I get refutations of size d, the degree of this big expander, times to the square root n over k, the number of layers. Okay, yeah, I think this got a little bit technical. I'm sorry if I lost, but I think, yeah, the main idea here was that, okay, in order to encode very large objects that I don't have the space to encode, I can implicitly encode them by encoding circuits. And I need one circuit for every time I need to evaluate the circuit. I need to have a separate copy. So that was the main idea. Okay, so to wrap up, yeah, so what I talked about here was, we know that we have this automatability of tree-like res k in time n to the k log n. We showed almost matching lower bounds. There's this log k factor, which is still there, and this is under randomized ETH. And then some open problems. Okay, so I think main open problem more related to tree-like systems would be to show this tight automatability for tree-like systems, like tree-like cutting planes, tree-like res parity. So these are systems where the same lower bound for tree-like resolution applies, but we don't have any upper bounds. So maybe we can prove a better lower bound. Well, another question is, yeah, can I improve that log k? That log k comes from the degree of the big expander. But maybe this can be improved. Also, can we weaken the assumption So the assumption used here was RETH, random ETH, but maybe, yeah, are there any barriers to proving tight non-automatability under like just P not different, P different from NP, or can I get rid of the randomness in the ETH? And this basically comes down to, well, one way of showing it would be just to construct better expanders deterministically. And I think in general, this is a very hard problem, but maybe in the setting that we have here, it could be slightly easier. I don't know. Okay, that's it. Thank you.